Welcome to the Solid Principles series, where we'll go over object-oriented principles that make us better software architects and developers. Let's dive in. Let's have a look at the solid principles of object-oriented programming. We have a number of them. We have the single responsibility principle, which basically states that there should never be more than one reason for a class to change. Each class should only have one central responsibility. Then we have the open-close principle. Software entities should be open for extension but closed for modification. Then we have the Liskov substitution principle, which states that functions that use pointers or references to base classes must be able to use objects of derived classes without knowing it. The interface segregation principle states that clients should not be forced to depend upon interfaces that they do not use. And finally, we have the dependency inversion principle, which says that you should depend on abstraction, not concretions. Let's have a look at this in detail. First, let's look at the single responsibility principle. There should never be more than one reason for a class to change. Each class should have only one central responsibility. For example, it should only deal with persistence, or it should only deal with pre- and post conditions, validation in other words, or it should only deal with notification, or only with logging, or only with formatting, or only with parsing, or only with error handling. The idea being that a class should not deal with any collection of these. It should specialize in one thing. Now, what about the open-close principle? That software entities should be open for extension but closed for modification. Let's have a look at an example. Let's say we have a simple calculator class, and this calculator class has four methods or four functionalities. It can add, it can subtract, it can multiply, and it can divide. But imagine that somebody comes to you right now and says, oh, but you know what? I would like to have a business calculator or a scientific calculator. What should you do? According to the open-close principle, you should not change the calculator class. You possibly already have code depending on it. What you should do is you should extend it. You should create new classes that extend the calculator class. So your loan calculator, which could maybe calculate some monthly payments or some future value of your mortgage, you just create a new loan calculator. Same thing with a scientific calculator. If you want to add sine, cosine, and tangent, don't put it into the original calculator class, extend it. What about the Liskov substitution principle? Functions that use pointers or references to base classes must be able to use objects of derived classes without knowing it. For example, if class A is a subtype of class B, then we should be able to replace B with A without interrupting the behavior of the program at all. Here's an example. If we create an abstract class shape, and then we create specific concrete classes like triangle, circle, and rectangle, any code that uses shape to get area doesn't have to know anything about the actual specific shape that it's using, whether it's a triangle or circle or rectangle. If I want to find out the area of something, all I need to do is ask for its area. I don't need to know specifically that it's any particular shape. That would be the Liskov substitution principle. And you can see that the idea is that if I have code that, for example, calculates all of the area of all the shapes on the screen, and let's say that I add a new shape, some sort of an oval or maybe a cylinder, my code that calculates the area shouldn't have to change at all. If it changes, that means there's something wrong with your architecture. It shouldn't change because it is still a shape. The next one is the interface segregation principle. Clients should not be forced to depend upon interfaces that they do not use. Declaring methods in an interface that the caller doesn't need pollutes the interface and leads to a bulky or fat interface. Let's have a look at an example. Let's say that I would like to create a logging functionality. So I create an interface called iLog. Notice that the interface has only one method, which is log. So now what I could do is I could simply just create a DB logger automatically, and I could create a file logger automatically. But then I need certain functionalities like open connection, close connection. I could add, for example, open connection to the iLog interface, but then the file logger, which would extend it, wouldn't need it. That's the problem. If I put the open connection and the close connection inside iLog, the file logger would be using a fat interface. It just doesn't need it. What we're doing is we're creating a generic iLog, and then we're creating sub interfaces, ID, blog, and iFileLog, which allows us to specifically create two classes, dblogger and FileLogger, that use exactly what they need to use. They don't have to use some extra methods or anything like that. That is what the interface segregation principle is all about. The last one that we have is the D in solid, is the dependency inversion principle, which basically says depend upon abstractions, not concretions. Imagine that we have a book service that creates a book. So we have two classes. We have a book service class and we have a book class. The book has a number, and this number needs to be generated. But because book service is the one that creates it, it would need to generate the number. Now, how would you do that? The best way to do it is to have the book service use an interface, which is an abstraction, that has a pretty generic method called generate number. Then, whatever number needs to be generated, the book service doesn't need to know what it is. The book service simply wants to generate a number. So whether the actual number generator happens to be ISBN generator or an ISSN generator is irrelevant to the book service. That is the idea. The book service depends on the number generator. It does not depend on the concrete elements. Now that we have gone over some theory, it is time to go over practical examples. In the next installments of this series, we'll look at the code samples in Java, Python, and Dart for each of the solid principles. See you soon. Don't forget to hit the subscribe button, give us a thumbs up, and ring the bell to get notified about our latest content. Thanks for watching.